Welcome back. Last week, we began with something of a project, a traffic management system. Where we left off last week was we wanted vehicles to evaluate their own way to a destination. Turns out this pathfinding evaluation warrants its own episode. Therefore, today we'll have a look at the AStar pathfinding algorithm. All right, welcome back. So we'll just go ahead and get started with this AStar pathfinding algorithm. We'll just also have a look at what we did, just have a look at what we did last week. All right, let's just go ahead and get started. Okay. Oh, and by the way, you'll also notice that Ravi isn't here with us again. He is still recuperating from his ankle injury. He did go to the doctor. There were no fractures or anything detected. He just requires rest. He'll be back next week. All right, so we had a look at this traffic management system, and we wanted, these are vehicles that are essentially going from one place to the other. That's what I was talking to you about in the introduction. Now we wanted these vehicles to essentially have like a source here and also have like maybe destinations on the other side. So they would go around, evaluate their own path and then take a U-turn and then come back over here. Now, if there were like roundabouts or anything like that, they would also find their way around a roundabout or make like a big U-turn around a roundabout and then go back. All right. And the whole point of this project is to see which one is better for traffic. Would it be better for traffic if there were just U-turns, or would it be better for traffic if we replace U-turns with roundabouts? All right. And so, like I was saying before, we require this AStar pathfinding algorithm so that these vehicles can essentially go around stuff. All right. That being said, what is this AStar pathfinding algorithm? So now I do have like a calculator sheet, an Excel sheet. And what happens? Okay, so let's just take a look at this grid that I have designed. All right. So let's say this is so I have a grid, and on this grid I have like a start point and an end point. All right. And you're asked to basically find a path from the start to the destination. The easiest way to do it would just be to go this y distance and then the x distance. Essentially tracing out a triangle. But as you know, as you might have already realized, this is not the most efficient path. The most efficient path would be a diagonal or the hypotenuse of this triangle, and therefore it would be this. All right. So how would you have like an algorithm determine this? This is like the most simplistic cases that you can think of, where it's just a grid. You just have to go from a source to a destination. But if you look at this, it's not going to be that simple, is it? Now, because there's going to be a divider, and this divider is not going to be all open. There are going to be places. There are only going to be specific places where you can take a U-turn. All right. So what I mean by that is that there are going to be blocks. So let's assume that these black things over here, or the black squares over here, are the blocks through which you cannot get around. So how would you do it? Yes, the path over here traced in blue would simply go around the block. But how would you write a pathfinding algorithm that goes around the block? Turns out it's a little bit easier than you'd imagine. All right, so there is this algorithm called the AStar algorithm. This is derived from the Dijkstra algorithm. Let me just open up Wikipedia, and I can show you what the Dijkstra's pathfinding algorithm is. All right, so all of these pathfinding algorithms are used to find paths around a graph. All right. So if there was a graph like this, what would be the shortest path between, let's say, this 1 and 5? That's what it was originally meant to do. But this can also be extended to a grid, because essentially a grid is also a graph, or is a form of a graph, and therefore it would work for grids as well, for our purpose as well. The idea is that I would just replace this grid with the road, or I would overlay this grid on top of the road, so that we can have like a nice proper pathfinding algorithm. All right. So you can read about the Dijkstra's algorithm. It's got a weird spelling, so don't mind that. It's pronounced Dijkstra. All right. So one of the derivations of this Dijkstra's, or an improvement of the Dijkstra's algorithm, is the AStar think it's just AStar search algorithm. It's an improvement over the Dijkstra's algorithm, and it uses something called as heuristics to essentially get around to get around Dijkstra's inefficiencies. All right, we'll just talk about that in just a moment. All right, so for the moment, let's just get back to our sheet and let's look at what we have over here. So once again, I have the start and I have the destination. And how do you evaluate this? So these yellow squares over here are the ones that I'm evaluating for. So I evaluate a score, and the score is essentially a sum of how far am I away from the start plus how far am I from the destination. And for each one of these neighboring squares or the block that I'm currently evaluating for, I determine a score. Now in this case, the one that is closest to the destination would obviously have like the lowest score. So in the next iteration, what you do is that becomes the current block. So that is actually a path that you have determined. All right. All the other blocks, we will place them onto a do not visit list or a closed list. All right. So what is a closed list? It means those positions have been evaluated. I do not have to evaluate them again. That's what it means. Next, you once again find all of the neighbors of this guy and you find out the scores once again. So I have all of these scores evaluated. Obviously, this is the most closest to the destination. All right, so that would have the lowest score, and therefore that would become once again the current block or the block that we'll have to evaluate against, and so on and so forth. You'll see that in the next iteration, I still have, you know, these values over here, this being like the shortest. Now, what happens if we continue with this and encounter an actual block or a divider? You know, in this in the case of a road, a divider. So this would be our block or a divider. What happens if we encounter this? All right. So this algorithm essentially would just so who are its neighbors now? It cannot get past, let's say, these. Let me also add a block over here so that it cannot get past the diagonal, because because the way we have designed this AStar or the way we treat our neighbors. Let me just go back to this one. You can see that we also treat our diagonal squares or our diagonal blocks as neighbors. All right. It is essentially possible for you to just change the neighbors and just have the top, right, left and then bottom to as neighbors. But in this case, we have evaluated all surrounding blocks as neighbors. All right. So getting back, so how would you evaluate this? So the only available blocks in this case would be this and this. So let me just mark them. So these would just be our blocks. What would be the scores that you would have? Which one is closer? Which one do you think is closer? I would say this one is closer. So I'm going to give it a lesser score than the current one. So let's say I call this 9, and this one I would say is a little bit distant. So this would still be 10. So in this case, our next block or the current block in the next iteration, if I can just do a copy of this one. All right. So that being done, all of these would become non-visitable, and this would become our current block. And this would become our current block. Now, so you can see what happens over here with this pathfinding, with this AStar pathfinding. All right. So it will now start to evaluate its neighbors until it reaches here, and once it reaches this block, it's just a very straightforward path to the destination. All right. So every time, so let's just go back to the beginning and let's just go back to the second one. So remember that this was also the start, this square that okay. So let me just call this, let me just mark it as green just for now. Every time I change the current block or I mark a new block as the current block, what would happen is that it would maintain a way back to where it came from. All right. So that would also be done. So this element over here or this block over here would maintain where its parent is. So therefore, finally, when it reaches its destination, when it reaches its destination, you would have a trace back all the way to its parent, and that trace back would only have like the most efficient route or the most efficient route. All right. Now this is actually very similar to the Dijkstra's algorithm. But what happens is in the Dijkstra's algorithm, you just have a score based on these scores that I'm showing would just be based on how far away you are from your source, but not to the destination. What AStar does is that it evaluates both the distance from your parent or the distance from your parent and the distance to the destination. This distance to the destination is essentially called as the heuristic score. All right. So let me just minimize this and I'll open up the pseudocode. Let's see what the pseudocode looks like. Now, before we go to the pseudocode, let's just look at what the AStar algorithm requires. It requires a score from the current block to the new evaluated block. All right. So it requires a score from the current block to the new evaluated block. So that's the G score and the H score. A score from the newly evaluated block to the end block. All right. So from a score from the H score. The G score is essentially from the current block to the newly evaluated block, and the H score is the newly evaluated block to the end block. All right. And the F score is essentially an addition of the G score and H score. As simple as that. Now, what is this H score? The H score is actually the heuristic score. Instead of looking at all of the blocks and looking at how far away the destination is, the heuristic score is just saying, is a way of saying, let me just estimate the path to the destination instead of going through all the blocks and finding out what the score is. It's just a way to estimate to the end. That's all. It's just a very rough estimation. That's all it is. All right. And now there are many ways. Excuse me. Now there are many ways to actually determine the heuristic score. Many algorithms use just a simple distance formula, but in our case, I'm using the Euclidean distance, essentially the hypotenuse between the current block and the destination. That's all it is. All right. So let's just have a look at the pseudocode itself. I'll upload all of this along with the source code and the link of all of those should be available in the description. All right. That being said, let's look at the pseudocode just a little bit. All right. I just want to make sure that it's a little bit big. All right. So I have, I'll create an array, something called as the open set, and I'll also create something called as the closed set. What is the closed set? Remember when we talked about this? All of these are already evaluated. I do not need to evaluate them again. What do I mean by that? It means, let's say this is the current block. I don't need to evaluate its neighbors, which we have evaluated in the previous iteration. So we don't need that. So that's the closed set. I'll also have something called as the G score, and I'll also have something called as the F, something called as the F score. Now we'll initialize the G score to essentially 0. G score is also an array, and it will contain the G score for every block. And we'll also have something called as the F score. Once again, for every block on the grid, we'll have an F score. All right. So now remember, when we are starting this AStar search, we are creating this open set, and we are putting the start block or the start to this open set. All right. So while this open set is not empty, make the current. So we'll have something called as a current block. So the current block would be the node in the open set having the lowest F score. Now, if this is the first time, if this is the first iteration, it would obviously be just the start block. So you'll have the start block. Remove that current block from the open set. So you have the open set removed from the current set, and essentially we are going to be adding it to the closed set. All right. So for each in the neighbor of current, so now you have the current block. For each neighbor, find out what their find out what their scores are. Find out what their or just calculate what their scores are. So we'll have something called as the tentative G score, which is nothing but the current G score or whatever G score I have plus 1. Because remember, I'm just adding arbitrarily. I'm sorry, where was I? I'm sorry about that. All right. So so remember, we are just dividing this entire canvas into a grid, and a grid consisting of blocks. And I'm just going to move one block by one block. So I'm just arbitrarily adding one over here. There are many other algorithms or many versions of this algorithm require you to find out the distance between this block and the the current block and the previous block. But for our purposes, we'll just add one. So now find out if this tentative score is less than the G-score of the neighbor. All right. So if it is less than the G-score of the neighbor, this new tentative score that I have, that becomes like so we just essentially calculate the G-score and the F-score, which is nothing but the G-score plus the heuristic score. All right. And if the neighbor is not present in the open set, we just add it to the open set. All right. And you keep on doing this, and and at the beginning of this one, you find out if the current has reached the goal. All right. So remember, at this step, at the first step, you're seeing the current is the node having the lowest F score. All right. But if that current becomes the goal, just reconstruct the path from where from the current path to where you came from. All right. And what do I mean by that? It means that, let's say, for example, in this iteration, I have found out a way over here, and the current path happens to be the end path. If it ever comes to that, we'll just have to make sure that we trace a way back to wherever we came from. That's what essentially we are doing. That's what essentially happens in this one. All right. Okay. So now let's go ahead and get started coding with this. All right. Let me close all documents that I don't need, so that I don't have a lot of. I'll keep the pseudocode open for now. I do not need this, I believe. I do need this. I do not need this. Yeah, I'm sorry, I'm taking some time with this one. All right. As with every week, I have some. I already have the HTML, the canvas, and everything ready. All right. What do I have? I have two JavaScript files this week. So I have something called as block.js and the astar.js. We'll just have, in a moment, we'll just look at that. I have a canvas, which I'm calling as the path canvas, which I'm giving like a specific width and height and everything. All right. We all know what it looks like. In the AStar, I have, as per usual, I have the width, height defined. I have the AStar context. I have the canvas element. The one thing that I have changed or added over here is I have a function over here called resize canvas, which I have added to the CodeSpace API, which I'll also update in my GitHub repository. And essentially what it does is it just looks at the canvas element. If you require this canvas element to fit to the width of the window, then I find out what is the ratio of the width to height, and I make the canvas element the width and the height of the window itself. So we'll just look at what it looks like. So yeah, so this is my canvas, and if I was to adjust this and refresh this, you'll see that the canvas grows by that much. So now I have something to work with. All right, so I don't have to sort of worry about the size and everything over here. So if I do a refresh here, once again, I have a new size and everything. All right, so that's what I have. Do I need this div? I don't believe so. Anyways, all right. So there you go. Now let's talk about the block.js class, the block class. In the block class, I have a constructor. The constructor takes an X and Y location because I'm going to divide this canvas into a grid consisting of blocks. Now I have the X and Y, the X and Y location of this block. I also have the following properties. Is blocked. What is blocked? Yikes. Why did I close the Excel sheet? I knew I was making a mistake closing it. What was I talking about blocked? This is what I mean by blocked. All right. So if this block is indeed blocked, which means you cannot get past this, we have a flag for that. We also have a flag to determine if this is the source, if this is the destination. And I also have a flag called isPath. So when I'm finished doing this, what I want to do is I want to draw the path from the source to the destination. And just so that I can draw this path in a different color, I have a flag called isPath. Remember those three variables I was talking about, the F score, the G score, and the H score? I have variables for that too. And just like how you have a linked list, I also have this dot parent. I mean, basically, it is going to point to another block or the block where it came from. All right. So remember that when we are evaluating the A star, you have to remember your parent. All right. So in this case, this guy's parent would be this, and so on and so forth. So I have that also. I also have a function called render. Basically, the block becomes responsible for rendering itself, which takes in a context as parameter. And depending on if it is the source, if it's the destination, if it is blocked, or if it is path, I draw the block with different rectangle colors. They're all the same rectangles, and then I just draw them with different rectangle colors. Now let's go ahead and get started. So now I have something called as the block size, which I'm making. I'm just ensuring that each block is of size 20, and I have an empty array, which I will add values to. Just having some documentation open here. I have an empty, this is intended to be a 2-dimensional array. All right. So let's go ahead and get started with our blocks. All righty. Here we go. As per usual, I have I'll start with X. I'm not going to start with I and J because I'm going to be creating these blocks as something that needs to be added to the canvas. Therefore, they require an X and Y location. So where X is equal to 0, which means we start from the top left. X is less than the width of the canvas. X plus is equal to block size. Remember, we'll have to sort of go, block size. I have the same with Y. So Y is equal to 0. Y is equal to width. Y plus is equal to block size. That's my block. So now, I have the loop essentially ready. Just create something called as a row array. All right. So this is supposed to be my row blocks. Just create it as an empty array, and row blocks dot push new block of. What are the things I require to create this block? All right. So let's just want to look at, yeah. So what are the things that I require? So I'll just require like an X. I require an X. I require a Y. And then, is it blocked? I'll just say, no, you're not blocked. Is it the source? No, you're not the source. Is it the destination? No, you're not. I'm not going to be setting them as destinations as of yet. I'm just going to initialize them as false and then set them later. So now that I have the row blocks, I will push these row blocks into our main blocks array. So I'll just say blocks dot push row blocks. These are row blocks or column blocks. I don't actually care as long as I make sure that the outer loop is the width and the inner loop is the height. Almost made a mistake over there. I really don't care. All right. So that being said, let me just say console.log blocks. This is just to make sure that I am indeed creating a 2-dimensional array consisting of blocks. All righty. Let's see. Yes. So now I do have an array of size 68 containing 22 elements in each row. So if I was to, so there you go. So that's just the block number 1, and it has, so there you go. So those are all the values that I'm looking for. So yes, so this does have something that exactly what I'm looking for. All I have to do now is essentially draw these blocks and see what they look like, right? So let me just create a function, or do I just draw them here? Do I just draw them here? No. Just call it render grid. And what will be the render grid do? Say for where this is where you start with I and J and everything. I less than blocks dot length I plus plus. You know what? I'm just going to realize this. The air conditioner is pointing right at the mic, so they might be causing a little bit of disturbance. So I'm just going to point it up. And yes, thank you. All right, sorry about that. For where J is equal to 0, J less than, not block size, blocks of I dot length J plus plus, And what am I going to do? I'm just going to say blocks of I of j dot render it in this A star context. Hopefully I have not made any mistakes. So if I do this, there you go. That's my grid. That actually works. I can't believe it actually works. Anyways, let's do this. I'll say, which one do I make as the source and which one do I make as the destination? Aha, before I even go there, I'll say, let me create two variables, start block, end block, because these are actually never supposed to change, or no, they can change, but you will see what I mean in just a moment. I mean, I require them to basically keep track of where the start and the end blocks are. So I'm going to say the start block is the block on 1, 1. All right. And the end block is the one on the very end of the block. Let me make it, yeah, I mean, I have to say, that's the wrong variable name. I'm sorry. So what would be the end of the block look like? It would be just be the block dot length minus 2. I'm just going to take 2 in this case. And its y would be blocks of 0 dot length minus 2. So that would be my start block and end block. Now remember, just making these variables does not make any difference. I will have to say that this is the source and end block dot is destination is equal to true. All right, I will have to say that you are the source and you are the destination. So once I have that, there you go. So that essentially creates the start and the end block, just to make myself feel better, or just to make sure that the end is truly visible. I'm going to make it like this. So now I have the source, I have the destination. Let's also actually create some actual blocks, right? So that they don't get past, so that it's not an easy path from the start to the end. How do I do that? I'm just going to say variable I is equal to 0, I less than 150 arbitrarily. I'm just choosing that arbitrarily. And I'm going to say for 150 times, choose a random index where I is equal to parse int of random between 0 and blocks dot length minus 1. Take a random value. The same goes for j, blocks of 0. Take a random value, and if this blocks of I comma jj dot is source, if it is not the source, we don't want to inadvertently block the source or the destination. If it is not the source and if it is not the destination, blocks of I and jj, I'm glad I spotted that, dot is blocked is equal to true. There you go. All right. So now if I do that, there you go. So those are some blocks that it will have to get around. So if it was like a pathfinding algorithm, it would have to like go around. It's not a straightforward route. So it would just have to go around and everything. So there you go. So now, so we have that ready. All right. What do I do next? Do I just have, oh yes, there is one thing that I'm forgetting. Let's have a look at the neighbor indices. We've done this many times over the previous episodes, but essentially let's say this is the current block and it is surrounded by grid. And it is surrounded by these grids. What needs to happen is that I have these offsets, and these offsets need to be declared. So these neighbor offsets need to be declared. So if I have a block and if I say, okay, go find me your neighbors, I'll have to go and say, okay, get me all of these indices, or get me all of these blocks that reside at these indices. That's what I'll have to do. All right. Okay, so I'm just going to go ahead and copy this and create an array out of it. Let me create an array out of this, right? So that would be its own array. So that's a two-dimensional array. So that's a two-dimensional array consisting of all of the neighboring indices. All right. So I'm just going to go ahead and declare this as such. I'm just going to say where there you go. Just going to make them look nice and tidy. There you go. So those are my neighboring indices. Oh, forgot a comma here. Am I forgetting anything else? So comma. So that's a two-dimensional array containing all of my neighboring indices. Let me also create a method called find indices, or find neighbors, I'm sorry. You will see over here. So given a block, find out where my neighbors are. That's the intention over here. I'm just going to look up some documentation from earlier. Okay, so now I have, so I essentially require to find out the neighbors of this block. So this block is somewhere on the grid, all right, and a block can only be ideally identified with its X and its Y location. So I essentially require to locate this block within the grid. Remember, for the block, I don't know where it is on the X and Y axis. So I'll just use my trustworthy for loops to essentially find out where this block is. All right. So for, do I also, okay. Yeah. So now that I have the block class, can I do something like this? Let's create a function called same as another block. I'm going to need this in just a moment. You will see. Now, what does this function do? This function says, is this block the same as another block that comes as parameter? That's all it needs. So if this dot x is another block dot x, and if this dot y is another block dot y, then return true or else return false. That's all I need, right? Yes, actually that's all I need. Now let's go back to AStar. For where I is equal to 0, I'm going to require this. Maybe I should just copy it somewhere and keep it. So now I have variable I equal to 0 blocks dot length. Yes. If a block dot same as blocks of I of j. Now, if it is the same as this block, then I know that this block resides within the grid. It resides at location I and j. All right. So I require variables to essentially store that. So let's say variable, let's say found I and found j, which are initialized to nothing. So I'll say found I is equal to I, found j is equal to j, and I'm also going to break out from this loop. All right. Now I am breaking out of the inner loop, but there is nothing that stops me from breaking out from the outer loop, and I don't want that to happen. So I'm going to create a Boolean variable here called found is equal to false, and if this is found, if found break out of the outer loop. What is that? That's it. All right. I'm just going to say, yeah, man, it's found. So I find it and it breaks out of the loop. So now I have the indices. I have the indices or the index of this block within the grid itself. All right. So what that means is that I have found this block. Now I take these neighboring indices and I return the other blocks as well. I'm going to create an array called neighbors, which is essentially just going to be an array of blocks. Let's say for where I is equal to 0, I less than what? The neighbor indices dot length I plus plus. Okay, so where ni, I'm just going to, so this is the neighboring I is equal to neighboring indices of I plus what? It would be plus the found I, right? I'm sorry, this would be I of 0 of plus found I, and the same goes with j. It would be I'm sorry, it would be 1 of found j, because remember the neighboring indices itself is a two-dimensional array of I comma 0 would be the first element, second element would be 1. All right. Yeah, so each neighboring index would consist of two items, the I and the j. So that's what it essentially is. So now I have the I and j. I'll just have to make sure that if the neighboring index is greater than or equal to 0, and the neighboring I is less than or equal to blocks dot length minus 1, and neighbor and j is greater than or equal to 0. Sorry about that. And n j is less than or equal to blocks of 0 dot length minus 1. You know, only if it is within bounds, then you can say neighbors dot push what? Push this block, right? Blocks of ni nj. There you go. I think that should do it. And finally, just return the neighbors. I think that should do it. Am I right on this one? Just going to look up some documentation here. Yes. I hate this dead silence, you know, that happens. Yes, I think I'm right. There is an easy way to there is actually an easy way to. Let's do this. Let's just go back to our grid, refresh, so that I have all of the things. I can say get neighbors of blocks of 2, 2. Get neighbors. Why is it saying, oh, I'm sorry, it's called find neighbors, of course. Find neighbors of a block that resides at 2, 2. There you go. So that gives you all of the blocks that are its neighbors. It shouldn't actually include itself. It won't. There would be essentially 7 neighbors excluding itself. So that's 1, 2, 3, 4, 5, 6, 7, 8. No, there would be 8 neighbors. Yeah, that's correct. So that's from 0 to 7. I'm sorry, I forgot about array indices. All right, so there you go. So now I have a method to find the neighbors. What else do I need to get started with the AStar search? Shall we just go ahead and get started with the AStar search? I also have the same as I have the find neighbors. Yeah, let's go ahead and get started with the AStar search. So I'm going to call this function AStar search, and just like what the algorithm requires, you require something called as an open set and a closed set. The open set will be initialized with the start, so we're going to do just that. Is basically nothing, where closed set is also nothing. Okay. Is also, yeah. So the closed set is also nothing. Yes. So what does open set get initialized with? Open set dot push. Push what? Push the start block. All right. So while open set dot empty, is it no, open set dot length is greater than 0. So while it is greater than 0, next, let's just go back to the algorithm. We'll have to, so we already have the G score array and the F score because each block maintains its own F score and G score. We don't have to create separate arrays for that. All right. Yes. So what's the current? Yeah. So just going to call it the current block is equal to open set of 0. I'm just saying, right now I'm just going to go ahead and get started. I mean, so the current is the node in the open set having the lowest F score. In this case, I'm just going to initialize it with 0, but I'm going to say for where I is equal to 0, I less than open set dot length, I plus plus. We require to evaluate all of them because remember this open set is essentially going to be growing. So if open set, what is open set? It's basically just blocks dot f is less than current block dot f. That's what it essentially means. Then current block is equal to this open set of I. All right, does that make sense? So the current block is the node in the open set having the lowest F score. All right. So yes, so this is the same as essentially finding the minimum of a given array of numbers, and so we do that. All right. What's the next one? If the goal has been reached, then we reconstruct the path to the parent. All right. If the current block is the same as the end block. What is the same as function? Remember in the block.js we created the same as. Perfect. That works so nice for us. If the current block is the same as the end block, that's it. We've reached the end. And return. This is the return condition of the function. Yes, this is the return condition of this function. So if it is the same as that, we'll say where current is equal to it's just a temporary variable to hold the current block. Yes. So the final path will essentially contain the path to the, say, while current dot parent is equal to null, right? So so while current dot parent. I mean, you don't have in JavaScript, you don't have to evaluate this null business and anything, because if it doesn't have a null, I mean, if it doesn't have a value, it will just return anything. I can just say final path dot push of current, just like a linked list, and then current is equal to current dot parent, just like a linked list, and then return final path. All right, so that will essentially return the path to the parent. Now what do I do? All right, so let's just go back. Now we'll have to remove the current from the open set. So how do I remove something from the open set? Oh yes, so I'm going to create another function called remove from set. Remove from set. Give me and remove what? Block. Okay, so I have a list. I'll have to remove this block from the list. All right, I'm going to be using this, I think, yeah, so I'll just call this remove from list instead of set. Just going to rename these as, yeah, this one. Okay. Where new set, and then where for I equal to 0, I less than a set dot length I plus plus. If a set of I dot same as block, if it is the same as that block, if it is not the same as that block, new set dot push a set of I. All right, and then finally just return new set. So what does this do? remember, there is no easy way for me to remove something from an array. I mean, I know that there is the splice function, but I don't. So what? So remember this one. So it says open set.remove current. I don't know where the current is in the open set. I mean, for all you know, the current set is going to be populated with all of these neighbors that are still being evaluated. And I want to remove this specific current block from the open set. That's what it essentially, that's why I need to find out, if it, find out where it is in the current set and then remove it. So splicing would be a little bit difficult. So the easier way for me to do it is to create this function called remove from set. So once I have this, wait a minute. Should this be, yeah, I think this should be within this. Sorry. So yeah, so it should be within the while loop. So there you go. So now first remove from set the open set, the current block, add this one to the, add the current block to the closed set. All right, because remember, we will have to add them anyways. So where is my closed set? There you go. So that's my closed set. So yeah, so why am I adding it to the closed set? It just essentially means don't ever evaluate this current block again, because we're going to the next, or we are evaluating a new block. All right. So closed set, am I calling it set or list? Yeah, I am calling. So closed set dot push current block. All right. So yes, so there you go. So now I'll say variable neighbors. So what is that? Yeah. So for each neighbor of current, all right. So which means I'll have to get the neighbors. Remember, we wrote that function find neighbors. Say find neighbors of the current block, and I'll say for and variable I equal to 0, I less than neighbors dot length I plus plus. All right. So now I have for each of the neighbors, I loop through them. All right. I'm just going to look up something real quick. All right. Yeah, I think we're good. I just have the pseudocode written down in like a more proper manner over here, which is what I'm looking at. So yes. So if So what does this say? If okay. So for each neighbor of the current. We find out if it is in the open set, right? So if oh yes, I will also require a function to determine if a block is in a given set. So I'm going to create another function is in set set a block. All right, which is essentially the same thing, I think. All right, for variable I equal to 0 or the set dot length, if a set is the same of I is the same as a block, then just say return true, or else just give me a false. All right. So now I have this function. If isn't set, what set? Should I check? Okay, so basically I should not be checking neighbors that are in the closed set, because remember, if you go back to our algorithm, let's say the newest current block is this that is marked in green. All right. When you evaluate its neighbors, remember there is a potential that these blocks that I'm highlighting are also its neighbors, but we should not evaluate them. Why? Because remember they belong in the closed set. So if it is in set of closed set, comma this block, right? I mean neighbors of I, or this neighbor is blocked. If it is blocked, don't even evaluate this. All right. So if if the neighbor that I'm evaluating is in the closed set, or if it is blocked, don't even evaluate it. Just move on. All right. What's next? Next, we'll have to calculate a G-score. All right. This is our temporary G-score that we are maintaining going back. So I have this tentative G-score. I'm going to call it G-score is equal to what? It would be the current block's G-score, plus 1. The current block dot G plus 1. Remember, in our case, inside our block, we're just calling the G score as G. So I have the G score plus 1. All right. Next. Now, if not is in set, okay, so if this current block, or if this neighbor is not in the open set, okay, is not in set, open set, neighbors of I. Am I doing this right? Yeah, if it is not in this open set, then I can just go ahead and say, yes, I can just go ahead and evaluate its new F score. I think that's what, yes. Okay, so just going to say neighbors.I.h is equal to, I need to find out its heuristic score. All right. Heuristic score between what? Between this neighbor and the end block. So I'm just going to evaluate this and keep it separately. Now, what is this heuristic score? Once again, I'm going to require a new function for this. Heuristic score between a block 1. I'm just going to call them block 1 and block 2. This is so simple because all we have to say is use our inbuilt get distance. What do I mean by inbuilt? I mean, in our code space API, we have a get distance function that is essentially just the hypotenuse. So I can just say get distance of block1.x, block1.y and block2.x and block2.y. That's it. So this will give me the heuristic distance. So I can just use this and I can say of the neighbor. So remember, heuristic score is always the distance between the neighbor or the one that is being evaluated to the end block. Remember, the end block will always remain constant. All right. So I have that. Now, if it is not in the open set, now, what do I mean by open set? Okay, so essentially what happens is, let's say this is the block that is being currently evaluated. The neighbors which are not yet evaluated are going to go and sit in the open block or in the open set. So the neighbors, if they are not there in the open set, then just evaluate their heuristic score. All right. Else we do what is specified over here. So if our tentative G score, in this case, else if our G score, I'm sorry, did I just copy the else if G score is less than the neighbor's G score? Am I doing this right? Yes. Else if G score is less than the neighbor's G score. Okay. Yes. So so what needs to happen if its score is less than the G score? Then we need to essentially do this one, right? Set the F score, a new G score, and all of these things that we need to do. All right. So remember, this neighbor is not in the open set. We are just adding it over here. Hey, maybe I can just do this, right? Instead of doing it in the other way. Yeah, I can just say if the G score is less than the neighbor's G score, in which case our neighbor's G score would be like 0 or something. If it is not in the open set, then we'll have to add it in the open set. Yeah, that's correct. So we'll just evaluate our G score. So the neighbor's G score is equal to G score. The neighbor's H score would be this, and then the F score would just be the G plus H, right? Be the tentative score would be the G score plus the heuristic score of the neighbor. That's yes, yeah, that's it. Would be this G score plus the H score. All right. And if it is not in the set, all right, if the neighbor is not in the set, then open set dot that's it. I think we are about done over here with this AStar search. Oh yeah, I also forgot to set the parent. All right, so this neighbor's parent would be the current block. All right. So yes, so I have the G score, I have the heuristic score also, and then I have the F score. The parent becomes, and if it is not in the set, then open set dot push. Yeah, that's it. Open set dot push neighbors of I. Is that all is required from this one? Yeah, that's it. That's it. So now I have this while loop. Now what happens if it never gets out of this while loop or nothing is evaluated? Oops, what did I do? All right. Sorry about that. I'm all over the place with this. This is return neighbors, render grid. Just going to say return nothing if nothing is evaluated, or if you get out of the loop without doing anything, then just sort of, get out of the loop. Don't do anything. Otherwise, you will return what? I mean, remember that when this is evaluated, it comes back to the while loop, or it goes back to the beginning, and it says if the current and because it is in the process of finding out its most efficient neighbors, it finds out what the current block becomes the most efficient neighbor, and so on and so forth. And if that most efficient neighbor happens to be the end block, it will evaluate its parent, and then it will just return back. So yeah, so that's about it. So I have the AStar search happening over here. Hopefully, I don't have any issues. I don't have any errors. Let's see what happens. So I will. So once I have rendered the grid. So this is my init. Let's just say results is equal to AStar search. All right, this should essentially work. Just going to say console.log of results. Aha, we seem to be stuck in a loop because we are essentially just going around in circles over here. So there's some exit condition that we have not met. I've removed all of the console logs. I'm going to create a variable here called gscore is best. All right. So if it is the first time that it's entering over here, I'm going to set this flag gscore best is equal to true. I'm also going to say if gscore is less than the neighbor's, then the neighbor's gscore, also set it as true, but don't do anything over here. Yeah, don't do anything over here. I'm say if gscore best, only then set all of these values, because that's what I've done in my more refined pseudocode here. Yes. Yeah, that's it. Yeah. There you go. Those are all my blocks. That is actually my path. That actually worked. Can't believe that worked. All right. So now that I have the results over here, what I can do is I can say for var equal to I less than results I plus plus results of I dot is path is equal to true. I'm going to say this is the path. I'm just going to highlight them as path equal to true, and then I'm going to end it with a render grid. So I have this. What happened? Oh, am I not? Okay, so that's, where is my render grid function? So that's my render grid, which just renders it back. I less than results dot length. Sorry about that. Don't think I need this anymore. So there you go. So that's my path. That's my path that goes from the start to the end. You will see that this is the most efficient path that it has found. Let's put the blocks back again and see what happens. There you go. So now you can see that it actually tries and evaluates a much more, it tries to go around these blocks and then finds a path over here. So you can see that it actually works and finds a path around the blocks. Okay, now let's just go back over here and let's look at the neighboring indices. Now remember that I have set all of them as indexes. I mean, all of them as my neighbors, all of the surrounding 8 as my neighbors, including the ones that are on the diagonal end. But so there, which is why you can see that it finds these diagonal paths as well. But what if I told this algorithm that your neighbors are not your diagonal ones? How do I change that? That's very easy for me to change. So I'm just going to comment the, really hate it when that happens. All right, I'm going to comment the original indices, and I'm just going to say your neighbors are just the 4 on top, on the left. That's my left. On the top, left. This I believe is the right, and the bottom. Let's say I declare that these are my neighboring indices. Then what does the path look like? You will see that you will not find any diagonals. You will find blocks that look like diagonals, but are actually not diagonals, which is great, which means our algorithm is working great. So basically we are at the end of what we need to do. We have the AStar algorithm figured out. All right. What I want to do from this point is just to sort of, animate it so that it looks a little bit more beautiful. All right. Beautiful to animate or something like that. Just looks beautiful. So if you are, if you have everything that you need, then I think we are at the very end. Then you can basically, close this. We're basically done with the AStar pathfinding algorithm. But if you want to stick around to see how we animate it, then yeah, just go ahead and stick around. Let's see how I do this. I'm going to require a variable called variable results, and I'm going to have a variable called results index. So I have the results and the result index. The results would be actually stored in that global variable that I created. I'm going to set them. So yeah, so I do the AStar search, and then I do the isPath is equal to true, and I set them. And I'm going to say animate path. I'm going to call it animate path, which is going to be function animate path. All right. And what does it do? It just essentially says, it just says results of result index dot is path is equal to true. Is equal to true. Render grid. All right. I don't need this render grid here. I don't need this render grid here because the animate path is going to render the grid for me. So is path is equal. Yeah. So this result index, which needs to be initialized to 0, plus plus if result index is greater than results dot length minus 1. I mean, if it, and just say return, that's my return condition. And then I can say set timeout. I can use the request animation frame, I guess, but wouldn't, yeah, let's just use the request animation frame of animate path. Let's see what happens. Oh, now you see the problem. See, the problem is that the results are from the end to the start, right? They're from the end to the start. Oh my God. Right? So which is why the results, so that's why your parent is actually, the path is evaluated parent by parent. So it's evaluated in the reverse order. So we basically need to reverse the order to do this. So what do I do for doing this? I can just say results is equal to results dot reverse, or is it just results dot reverse? I think it's just results dot reverse. Yeah, there you go. So that's the results dot reverse. That's how it's supposed to be animated. So any new paths that you give, it'll just do this. Okay, so that was our pathfinding algorithm, AStar pathfinding algorithm. I really hope you enjoyed this as much as I enjoyed coding this. Please do like, share, and subscribe to our channel. We really like your support. Many of you have sent your emails requesting for the calendar. I have shipped them all out to you. I really hope you like them. From myself, from Ravi, and from CodeSpace, thank you for joining. See you all next week.